students, today I shall start the fifth part of this infrared spectroscopy. In my last lecture, in fourth part of infrared spectroscopy, I had discussed up to these terms, that is fundamental absorption, first overtone, second overtone and hot bands, etc. Also, these equations were also derived. Fundamental absorption is equal to omega E bar into 1 minus 2xe. First overtone is equal to 2 omega E 1 minus 3xe. Second overtone is equal to 3 omega E bar bracket 1 minus 4xe. And for hot band, it is equal to omega E bar under bracket 1 minus 4xe. Here omega E bar is a fundamental frequency and xe is an harmonic constant. Here numerical can be solved. How this anharmonic constant xe can be calculated? For this calculation, let us take an example. If fundamental vibration is 2100 per centimeter and first overtone is 4100 per centimeter, then calculate what will be the value of an harmonic constant xe. We already know from previous lectures that when the transition is from V is equal to 0 to V is equal to 1, it is called fundamental absorption, and it has very high intensity, and the value of this fundamental absorption is equal to omega E bar into 1 minus xe, as I have written in the previous lectures and also in this lecture also. V is equal to 0 to V is equal to 2 transition will be called as first overtone, and it has somewhat lower intensity than the fundamental intensity of fundamental absorption, and the value of this will be equal to 2 omega E under bracket 1 minus 3xe per centimeter. So according to the question, the fundamental vibration occurs at 2100 per centimeter. So we have written this value omega E bar 1 minus 2xe is equal to 2100 per centimeter, equation number 1, and the first overtone, which has value 2 omega E bar into 1 minus 3xe per centimeter, and that is equal to 4100, so equation number 2. Now with the help of these two equations 1 and 2, we have to calculate the value of xe. So it is nothing but only simplification. When we divide equation 2 by equation 1, we get this type of expression, and on simplification we get the value of xe is equal to 0.022, and it has no unit because per centimeter cancels out here, so there is no unit. To understand these terms, that is the equilibrium frequency and the anharmonic constant, we take another example, and from this example it will be very clear that how these two terms can be calculated. So let us take the example. The spectrum of HCl shows an intense band at 2886 per centimeter, a weaker band at 5668 per centimeter, and a very weak band at 8347 per centimeter. Then we have to calculate the equilibrium frequency omega E bar and the anharmonic constant xe. So according to the previous question, here again we can write, this is for fundamental vibration, this is called fundamental vibration, fundamental absorption, this is first overtone, this is second overtone. So according to the question, the intense band at 2886, so it will be definitely first a fundamental absorption, and then a weaker band at 5668 per centimeter, so it will be first overtone, and a very weak band at 8347 per centimeter, so it will be second overtone. So equations 1, 2 and 3. And now with the help of these three equations, we have to solve the value of omega E bar and xe, that is anharmonic constant. So First of all, what we do, we multiply equation 1 by 3, then we get this type of equation and it is written as equation 4. Now subtracting equation 3 from this equation 4, that is equation 4 minus equation 3. So here it is equation 4 and it is equation 3. So equation 4 minus equation 3 is equal to this one, and when it is solved, we get the value of omega E bar is equal to this one as equation 5. When this value of equation 5 is put in equation 1, if we put this value in equation 1, then we get this type of expression, and on further solution we get the value of Xe, that is an harmonic constant, as equal to 0.0173. It has also no unit. Now we have to calculate the value of omega E bar, and the value of omega E bar can be calculated by putting the value of Xe in equation 1. So on solving these expressions, we get the value of omega E bar is equal to 2989.43 per centimeter. So this is how we can calculate the values of omega E bar, that is equilibrium frequency, and Xe, that is anharmonicity constant. Now there are some more terms: addition band and difference band. So what is addition band? In addition to these fundamental bands and overtones, which we have already discussed, some combination bands arise due to the combination of these two conditions. First condition is, that is due to the combination of fundamental absorption peaks. If nu1, nu2, nu3 are the fundamental bands, then their combination will be like nu1 plus nu2, other combination will be like nu1 plus nu2 plus nu3, other combination will be like nu2 plus nu3. So this is one type of combination. Another type of combination will be like fundamental absorption peak and overtone, like 2 nu1 plus nu2. So this nu2 is the fundamental, but this 2 nu1 is the overtone. So when these two combine, they give some another type of band, and these are called as combination band, and these are also called as addition band. Similar to addition band, another band is also known as difference band, like nu1 minus nu2, because nu1 and nu2 are the fundamental bands and their difference gives to another type of band, nu1 minus nu2. Similarly, this nu1 plus nu2 minus nu3 will also give another type of band, and 2 nu1 minus nu2, that is, this is overtone and this is fundamental. So difference of these two fundamental band will give another type of peak. So these will be collectively called as difference band. So we have learned two another terms, an addition band and difference band. To get a clear picture of these two terms, that is, what is addition band like this and what is difference band like this, we can solve a numerical like this. Suppose this is a numerical. A triatomic wind molecule like this one, Ab2, exhibits following peaks in IR spectrum. What are the peaks? 519 per centimeter is very strong, 1151 per centimeter is very strong, 1361 per centimeter is strong. Also there are some other peaks. 1871 per centimeter is very weak, 2305 per centimeter is very weak, and 2499 per centimeter is moderate peak. Now we have to told to interpret these IR data. Okay, what these IR data says. First of all, we start from here, that this molecule which is given to us, Ab2, which is a bent molecule and is a non-linear and triatomic molecule, that is, here total number of atoms is equal to 3. So according to the rule, the number of fundamental modes of vibration will be equal to 3n minus 6, where n is the total number of molecules. So number of fundamental modes of vibration will be calculated as 3. That is, nu1, nu2 and nu3 are its vibrational fundamental modes. So since these three are very strong, 519, 1151 and 1361. So these are the fundamental modes of vibration, nu1, nu2 and nu3, 519 per centimeter, 1151 per centimeter, 1361 per centimeter. Next is that 1871 centimeter is very weak and 2305 centimeter per centimeter is also very weak. So band at 1871 per centimeter is very weak, hence it is a combination, means addition of bands nu1 and nu3. That is, if we add the frequencies of nu1 and nu3, it is equal to 519 plus 1361, it gives 1880 per centimeter, and it is near to 1871 per centimeter. Therefore, this band which occur at 1871 is a combination band of nu1 and nu3. Similarly, the band which occurs at 2305 per centimeter is first overtone of nu2 fundamental band. nu2 fundamental band has value 1151, and if we take 2 times of this value, we get 2302 per centimeter, which is close to 2305. So this band is actually first overtone of nu2 fundamental band. Now there is another band which is a moderate band, 2499. So if we see the values of nu2 and nu3, if we add the values of nu2 and nu3, we get the value 2512 per centimeter, which is very close to 2499 per centimeter. Thus, we can explain peaks which are obtained at different levels. So, how can interpret these IR data? Now, the another term we have to discuss is Fermi resonance. But before discussing the term Fermi resonance, we have to understand what type of different modes of vibration and how vibrations take place in these different modes. So, this is how in a pictorial diagram I have tried to explain this. What are different modes of vibration? So, there are 2 different modes of vibration initially. One is stretching mode and another is bending. Stretching means, if suppose this is a molecule, we can stretch it. So, it is a stretching mode, and if we bend it, if we want to bend it like this, then it will be bending mode. So, what happens in stretching mode and what happens in bending mode? In stretching mode, internuclear distance changes periodically. Suppose we take the example of this methane. If we take the example of methane, then what happens? We are taking only 2 bonds, remaining the other 2 constant. These 2 bonds are in the plane of this smart board, and one is above the smart board, above the plane of the smart board, and one is just behind the plane of the smart board. This is towards the viewer, and this is behind the plane of the smart board, and these 2 bonds are on the plane of the smart board. So what happens if the bond, CH bond, vibrates like this, that is internuclear distance periodically changes. This is also vibrating like this, that is internuclear distance is periodically changes, then this is called stretching mode. And in case of bending mode, what happens, that angle between the 2 bonds, suppose this is a pictorial diagram of CH4 molecule, and these 2 bonds, what happens, this is the angle between these 2, this is the angle between these 2 bonds, and if the direction of movement of bond is like this as shown in the figure, then what happens, the angle between them, these 2 bonds, gradually changes. Again, it comes back to its initial position, again the angle changes. So here I have written that in case of stretching mode, internuclear distance changes periodically, and in case of bending mode, angle between the 2 bonds having a common atom changes periodically. So this stretching mode is of 2 types. This stretching mode is of 2 types. One is symmetric stretching, another is asymmetric stretching. What is symmetric stretching and asymmetric stretching? Suppose this is a diatomy molecule. Here there are 2 atoms. They are connected through this bond. If this molecule vibrates in such a way that these 2 atoms goes equally on both sides and then come to its initial position at the same time, then what happens, that the stretching will be called as symmetric stretching. That is, we are stretching the bond with the same force of these two atoms. Again, we can also understand with this example. Suppose here it is a diatomy molecule. If we want to extend in equal distance, it comes to like this. Again, if this goes to its initial position, it comes like this. So this type of vibration is called stretching vibration. But suppose a diatomy molecule is like this. This is the center of gravity, and one is vibrating up to this position, another is vibrating up to this position. Then naturally there is no equal forces operating between these two, and this type of vibration is called as asymmetric vibration. Here from this figure we can also see that one is going on this side, another is going on this side. If we stretch the bond of one atom on this side and compress the bond from the other side, then also it is asymmetric stretching. Now bending mode is also of two types: bending mode of vibration in plane and bending mode of vibration out of plane. Bending mode of vibration in plane is of two types, that is scissoring mode and rocking mode. Scissoring mode, the word has come from scissor. Scissor is like this. Scissor operates like this. This is the action of scissor. If we want to close these two blades together, this is the action. If we expand these two blades away from each other, then this is the situation. So they are in the same plane. These two bonds are on the same plane of the smart board. They come close together and they far apart also. Come close together and far apart. Come close together and become far apart. But if such a vibration takes place that these two bonds go simultaneously on one side, then it is called as rocking mode. So these two vibrations are in the plane of this smart board. Another type of bending mode is out of plane. These two vibrational modes are bending vibrational modes are on the plane. This is on the plane of this whiteboard. But another type of bending mode of vibration may take place, which may be either out of the plane. Out of the plane means plane front side of the viewer, and another will be like back side of this plane. So this plus sign, this is represented by plus sign and minus sign. Plus sign and minus sign here does not indicate the sign on hydrogen atom. It only indicating the direction of the movement of the bond. Plus sign is taken that if we consider the plus sign as the bonds are moving out of the plane towards the viewer, then minus sign will be like the behind the plane of this smart board. So what happens if both these bonds simultaneously come on towards the viewer and it goes to on the other side of the plane, that is behind the smart board, then what happens? What will be the action of these two bonds? These two bonds will be like this. They are coming towards the viewer and going away from the viewer. Coming towards the viewer and going away from the viewer. And twisting mode, it is like just we have to open the bottle of a cork of a bottle. Then what happens? We have to hold the bottle from one hand and we have to twist the cap of the bottle in opposite direction. Suppose we are opening the cork of the bottle, then the direction of movement of the cork will be like this and the direction of the movement of the bottle will be like this. This is the direction. Here the movement of bottle is in this side, but the movement of the cork is in this side. So this is the twisting mode. So what happens that these two bonds, one bond is coming out of the plane and another bond is going behind the plane. One bond is coming out of the plane and another bond is going behind the plane. So if this type of vibration occurs, then it is like twisting, which is just like twisting or opening the cork of a bottle, and another is wagging. Wagging like just we are moving our head like this, coming in this side and going in this side. So this is a wagging mode of vibration. What is the energy requirement of these vibrations? Bending mode of vibration has the lowest energy. Then the energy comes of the symmetric mode of vibration, and asymmetric mode of vibration has the highest energy. Now, on the basis of the knowledge of these type of vibrations, that is symmetric vibration, asymmetric vibration and bending vibration, now we can discuss the term as Fermi resonance. Fermi is the name of scientist who primarily observed this type of phenomena, and it is named after his name as Fermi resonance. What is Fermi resonance? When the frequency of a fundamental absorption peak, when the frequency of a fundamental absorption peak and a combination band or an overtone, if the frequency of fundamental absorption band is same or it is equal to or approximately same with a combination band or with an overtone, then a resonance phenomenon occurs. What is resonance phenomenon? We know in physics that when two bodies or two particles have the same frequency, then they start vibrating with more amplitude or more frequency, and that phenomenon is called as resonance phenomenon. And due to the resonance phenomenon, what happens? Two new absorption peaks are up, and this phenomenon is called as Fermi resonance. I am trying to explain that a fundamental absorption peak and a combination band or an overtone, if they have equal value of frequency, then resonance takes place, and due to the resonance, two new absorption peaks are obtained, and this is called as Fermi resonance. Here the exchange of energy between the two modes of vibration takes place. As a result of, the energy of one mode of vibration increases while the energy of the other mode of vibration decreases. Since two modes are having the same value of frequency, so what happens? Exchange of energy takes place between these two vibrations, and one frequency gets a higher value and another frequency gets lower value, and this is the case of Fermi resonance. This Fermi resonance can be understood with the example of carbon dioxide. Let us take the example of carbon dioxide where Fermi resonance takes place. This is a linear molecule like this, and total number of atoms is equal to 3, and the number of total fundamental modes of vibration will be equal to 4 according to this formula, 3n minus 5. Out of these 4 vibrational modes, one mode is symmetric stretching. What is symmetric stretching? I have just explained. And another is asymmetric stretching. It is also explained here. And third and fourth are bending mode of vibration. So first one is given the name nu1, second given the name nu2, another nu3 and nu4. Here it is nu3 and nu4. You can write nu3 and nu3 because both have superimposed on each other. So instead of nu3 and nu4, you can write nu3 and nu3 also. And the values of peak are obtained as follows. This bending mode is 667 per centimeter. Asymmetric vibration mode occurs at 2349.3 per centimeter, and symmetric stretching is 130 per centimeter. Because here I have written that the energy of bending mode is lowest, then the energy comes of symmetric mode, and finally asymmetric mode has the highest value of energy. So this is also clear from here, these values. This is symmetric mode of, this is asymmetric, and this is bending. This bending has the lowest value, then the value comes of the symmetric mode, and then comes the value of asymmetric mode. Now what happens? Fundamental band of symmetric stretching, that is nu1, is occurring at 1330 per centimeter, and this value is approximately equal to the first overtone of fundamental band of bending vibration. Bending vibration occurs at 667 per centimeter. So if it is multiplied by 2, it is approximately equal to the first overtone. So when it is multiplied by 2, it comes equal to 1334 per centimeter, and this value is very close to the value 1330 per centimeter. So what happens? This mode of vibration and this mode of vibration, these two combine together, giving result to a resonance phenomenon. And what happens? Two new peaks are obtained. One peak has the higher value and one peak has the lower value. So these two peaks are obtained. One peak is obtained at 1285 per centimeter and another peak is obtained at 1385 per centimeter. So if we take the average of these two values, it comes 1335 per centimeter, which is equal to the values of this fundamental band, and this is overtone. So this is the Fermi resonance phenomenon. Similar to this example, another example is of aldehyde. This is the CH bond. Fundamental band of CH stretching and overtone band of CH bending resonate to give Fermi resonance at 2750 per centimeter and 2850 per centimeter. So thank you for today. In my next lecture, I will start the sixth part. It is a very long chapter, so I will try to discuss in different parts. So next part will be part 6 of infrared spectroscopy. Thank you.